slightly under 1,000 kilometres. That is how far the debris from Wednesday morning's collision on the Moon is modelled to travel, and almost nobody has reported it. At 2:35 in the morning, Eastern Time, on the 5th of August, a dead rocket stage the size of a 5-storey building hits the lunar surface at 5,400 miles an hour and throws more than 1 million kilograms of the Moon into space. You will almost certainly see nothing. All of it stays up there permanently, because that world has no air, no water, and no way to ever clean up after us. And underneath that number, 23 scientists wrote one more sentence about future astronauts that changes what this collision actually means. If that has your attention, hit the like button and subscribe to the Sky Lab, because what happens in the days after this impact matters far more than the impact itself. And drop me a comment telling me where you are watching from and whether you would still take a one-way ticket to the Moon. Now, let us get into it. Part 1. The collision we scheduled by accident. At 2:35 and 37.5 seconds in the morning, Eastern Daylight Time on Wednesday the 5th of August, something that human beings built is going to hit the Moon. Not approximately. Not sometime that morning. That second. The prediction has been public for 11 months. It has been refined 4 times, and the man who calculated it will refine it again before it happens. If you're in the Central Time Zone, that is 1:35 in the morning, Mountain 12:35, and if you're on the Pacific Coast, it happens on Tuesday night at 11:35 before the calendar has even turned over. What arrives is a dead rocket. Specifically, it is the upper stage of a Falcon 9, the second stage, the part that does the last push and then gets left behind. It has a catalogue designation and nothing else, 2025-010D, 12 metres long, 4 metres across. The astronomer who found it describes it as roughly the height of a 5-storey building, and that is a useful thing to hold in your head, because we are not talking about a bolt or a fleck of paint. This is a piece of industrial hardware the size of a small apartment block, and it is falling toward the Moon right now as you watch this. Its mass is somewhere between about 3,900 and 4,900 kilograms. I am giving you a range because the 3 teams who have studied this event assume slightly different things about how much propellant was left in the tanks, and the honest answer is that nobody knows to better than about 1,000 kilograms either way. It will arrive at 2.43 kilometres per second, 5,400 miles an hour, 8,700 kilometres an hour. There is no air on the Moon, so talking about a Mach number is technically meaningless. But if there were air, that would be about Mach 7. Now, that is the event, and if you have been watching this channel for a while, you already know most of it because we covered this collision last week when it was still a week away. That video was about the event itself, how one independent astronomer found it, why nothing exists to stop it, and what it says about the fact that nobody is watching the space between here and the Moon. This video is not that video. Because in the middle of July, a group of 23 scientists published a paper about this impact. It is an organising document, essentially a set of instructions for observatories and amateur astronomers on how to watch what happens on Wednesday morning. And buried in the 3rd subsection of the 2nd chapter of that paper, in the flat, careful, deliberately unexcited language that scientists use when they are trying very hard not to sound alarming, is a single sentence that almost nobody has quoted. The debris thrown out of that crater is modelled to travel up to nearly 1,000 kilometres. Let me put that number somewhere you can feel it. The Moon is 3,475 kilometres across. Its entire circumference, the whole way around the world, is about 10,900 kilometres. So 1,000 kilometres is not a local effect. It is not a debris field. It is nearly 1/10 of the way around an entire world, from one collision, from one dead rocket that nobody has thought about in 18 months. And the sentence does not stop there. It goes on to say that this is far enough to be significant from the perspective of presenting a hazard to future astronauts or infrastructure across much of the lunar surface. Future astronauts, infrastructure, across much of the lunar surface. That is the story, not the collision, the sentence. To understand how we got here, you have to go back to a launch that was, by every measure anyone was using at the time, a success. On the 15th of January 2025, a Falcon 9 lifted off carrying 2 commercial lunar landers. One was Blue Ghost Mission 1, built by an American company called Firefly. The other was Hakuto R Resilience, built by a Japanese company called ISpace. They were held together on the way up by a payload canister and all of it was pushed out of Earth orbit and onto a path to the Moon by the upper stage. 4 objects went up on that rocket, and they had 4 completely different endings. Blue Ghost worked. On the 2nd of March 2025, it touched down in Mare Crisium, the Sea of Crises, and did its job. The payload canister, the piece of structure whose only purpose was to hold the 2 landers together, came back down into Earth's atmosphere at 6 minutes past noon, Universal Time, on the 15th of March, and burned up over the border between Argentina and Chile. Nobody knows whether anyone saw it. If they did, it would have looked like a bright meteor and they would have had no idea what they were looking at. Hakuto R took the long way. It flew a slower, more fuel-efficient trajectory that took months instead of weeks, and on the 5th of June 2025, about 90 seconds before it was due to land, contact was lost. It crashed. And the upper stage, having done its one job perfectly, was left where it was. To be fair to everyone involved, that is what almost always happens, and almost always it is fine. More than 600 Falcon 9 rockets have flown. Most of their upper stages either sit in orbits close enough to the Earth that the thin outer wisps of our atmosphere drag them down within months or years, or they are deliberately deorbited and burned up on purpose. A handful have been placed into orbits around the Sun, where they will not bother anybody for centuries. The population of upper stages that end up in a high, looping moon-crossing orbit around the Earth is very small, because very few missions go that far out in the first place. This one did, because its payload was going to the Moon. That is worth pausing on. It was not disposed of. It was not steered anywhere. It was simply released, in a high, looping orbit around the Earth that happens to cross the orbit of the Moon. And then it was no longer anybody's problem, because there is no procedure by which it becomes anybody's problem. The orbit it was left in takes about 26 days to complete. At its closest to us, it comes in to around 220,000 kilometres. At its furthest, it swings out to around 510,000. The Moon sits at about 385,000 kilometres, right in between. So the stage has spent the last year and a half crossing the Moon's orbital path over and over again, roughly 14 times a year, and every single time the Moon has been somewhere else, until now. On Wednesday, both objects arrive at the crossing point at the same moment. That is the entire mechanism. Nobody aimed anything. Nobody targeted anything. 2 orbits intersect in space, as they always have, and after 18 months of drift they finally intersect in time as well. Where it lands is a place called Einstein. Lunar latitude 19.461 degrees north, longitude 93.293 degrees west, in a heavily cratered stretch of terrain just barely on the near side of the Moon, on the sunlit part of the disk close to the western edge as we see it from here. The Moon will be a little more than half illuminated, about a week past full. I want to flag something about those coordinates, because it matters for how you should hold every number in this video. That position comes from a solution posted on the 1st of August, 4 days ago. It will be updated again before impact, and it has already moved several times. On the 8th of June, an update moved the predicted impact point 170 kilometres to the northwest, and moved the predicted time 9 minutes earlier. On the 17th of July, another update moved it about 10 kilometres and about 2 seconds. The prediction is converging. It is getting tighter every week. But even now, 4 days out, the man doing the calculating will tell you flatly that he does not trust it better than a few seconds and a few kilometres, which is a strange thing to sit with when you think about it. We can name the second. We cannot quite name the spot, and if you want to go outside and look, here is what you are looking for. The Moon rises around midnight local time in the eastern half of North America on Tuesday night, with Saturn not far from it. By 2:30 in the morning it will be reasonably high in the southeastern sky. The impact happens on the right-hand edge as you look at it, the western limb on the lit side close enough to the boundary of the disk that the geometry is almost edge-on from our point of view. You will not see it. I want to be honest about that up front rather than sending several 100,000 people outside to be disappointed. Later in this video I will explain exactly why the people who study this for a living think Earth is probably going to record nothing at all, and why they are pointing 3 of the largest telescopes on the planet at it anyway, and none of that in the end is what should keep you watching. Because the impact itself is genuinely, provably harmless. Nobody is in danger. Nothing on the Moon is in danger. Every scientist involved in this will tell you so directly, and later in this video I'm going to quote them saying it, at length, because the honest version of this story is stronger than the frightening one. The reason this matters is that on Wednesday morning, for the first time, a group of scientists gets to measure something they have been forced to guess about for 67 years, and what they are measuring is not really about Wednesday at all. It is about a decade from now, when the moon is no longer empty, and a number like 1,000 kilometres stops being an interesting line in a preprint and starts being the distance between somebody's home and somebody else's garbage. So let us go and read that sentence properly. Part 2. The sentence nobody reported. The paper was posted on the 16th of July 2026. It is a preprint, which means it has been made public before formal peer review, and there is nothing unusual or suspicious about that. It is standard practice in astronomy, particularly for anything time-sensitive, and this is about as time-sensitive as science gets. There was no point waiting 6 months for review on a document whose entire purpose is to tell people where to point their telescopes on the 5th of August. It is released under an open license, so anyone can read it, and it carries a release number from Los Alamos National Laboratory, which is the kind of institutional stamp that tells you a legal department has looked at it. 23 authors. I want to walk through some of them, because in a story like this, the credibility of the people involved is not a footnote. It is the whole foundation. The lead author is Benjamin Fernando at Los Alamos. Jennifer Heldman and Anthony Colaprete are at NASA Ames Research Center. William Cook is at NASA Marshall Space Flight Center, where he runs the office that studies what hits the Earth and the Moon from space. There are 4 researchers from the Johns Hopkins Applied Physics Laboratory. There is a seismologist from the University of Maryland. And beyond the American institutions, there are co-authors from South Korea's Aerospace Research Institute, from Italy's National Research Council, from the Technical University of Munich, and from the University of Aberystwyth in Wales. And there is one more name on the author list that tells you how small this field really is. Bill Gray, the independent astronomer who found the object in the first place and calculated that it was going to hit. The person who predicted the impact and the people planning to watch it are co-authors on the same document. That is not a conflict. It is just a reminder of how few people work on this. Before we get to the sentence, it is worth understanding why a group this senior cared enough to organise around a piece of falling garbage in the first place, because the reason is genuinely interesting, and it is not what you would guess. Artificial impacts on the moon are rare. The paper's own phrasing is that they have occurred only a handful of times ever, and they are scientifically precious, for a reason that has nothing to do with spectacle. When a natural meteoroid hits the moon, you have no idea what hit it. You do not know the mass. You do not know the density. You do not know whether it was a solid chunk of iron or a loose clump of dust held together by nothing much. You see a flash, and everything you conclude from that flash depends on assumptions you cannot check. An artificial impactor is different. We built it. We know its mass to within 1,000 kilograms. We know its dimensions to the centimetre. We know its composition. And thanks to 11 months of orbital tracking, we know its velocity to within meters per second. It is what physicists call a controlled source, and controlled sources are how you calibrate everything else. The Apollo program understood this perfectly. Between 1969 and 1972, the upper stages from Apollo 13 through 17 were deliberately crashed into the moon, along with several of the lunar modules once the crews had transferred back out of them. This was not disposal. It was an experiment. The astronauts had left seismometers on the surface, and firing a known mass into the ground at a known speed at a known moment gave those instruments something to measure that nobody had to guess about. The data from those deliberate crashes is still being used today to work out what the inside of the moon is made of. That is more than half a century of scientific return from throwing rockets at the ground on purpose. But there is a gap in that record, and it is the gap this paper is trying to close. None of those Apollo-era impacts produced a confirmed flash observation, because the camera technology of the time simply could not do it. Which means that in all the decades since, every model of what an artificial impact looks like from Earth has been calibrated against nothing. Now here is the sentence. I am going to read it exactly as it appears, because the precision of the wording is the point. The maximum ballistic range of resolved particles is found to be slightly under 1,000 kilometres, which is far enough to be significant from the perspective of presenting a hazard to future astronauts or infrastructure across much of the lunar surface. There are 2 words in there doing an enormous amount of work, and almost no coverage of this event has explained them. Resolved particles. A computer simulation of an impact does not track every grain of dust. It cannot. There are more grains in a cubic metre of lunar soil than there are stars in the visible universe, and no supercomputer that has ever been built could follow them all. So the model divides the ground into cells, and the size of those cells sets the smallest fragment the simulation is capable of seeing. In this case, that limit is about 37 centimetres. Anything smaller than 37 centimetres is invisible to the model. It exists in reality. It does not exist in the calculation. And here is where you need to pay attention, because the direction this runs is not the direction you would expect. The paper states, in its own words, that the smallest debris fragments are the most numerous, and that they are the most rapidly ejected. The smallest pieces are the fastest pieces. That is not a guess. It is a basic consequence of how energy distributes itself through fragmenting material, and the authors say so plainly. Which means the 1,000-kilometre figure describes only the big, slow chunks that the simulation was able to follow. The fast material, the fine material, the stuff that actually travels, was never in the calculation at all. The number is a floor. It is not a ceiling. I want to be careful here, because it would be very easy to take that and run somewhere irresponsible with it. So let me tell you what the paper says about its own limitations, in its own voice, before anybody accuses this video of doing the thing it is specifically trying not to do. The simulation is what the authors call an axis-emmetric, vertical, end-on impact. In plain terms, they modelled the rocket coming straight down, nose first, perfectly symmetrical. They describe this themselves as an end-member case, which is scientist, for we know this is not what will actually happen, but it brackets the problem usefully. The real impact will come in at an angle, and here is a small, honest wrinkle that a more careless video would smooth over. The paper says the impact angle is 34 degrees from vertical. Bill Gray's own page says 31 degrees above the horizon. Those two statements cannot both be true. 34 degrees from vertical is 56 degrees above the horizon, which is nearly twice as steep. Neither team has publicly reconciled it. It probably comes down to two groups measuring from two different reference lines, and nobody catching it, which happens constantly in science and is usually harmless. But when the geometry of the impact determines which direction the debris goes, it is not nothing. Then there is the run time. The whole simulation covers 9/10 of 1 second. That is not a criticism. It is a straightforward consequence of how expensive this kind of modelling is, and the authors say explicitly that 9/10 of a second is long enough for a transient crater to form, but not long enough for the crater to finish forming. Every ejector number in that paper comes from less than 1 second of modelled time on a computer, describing an event nobody has ever measured, and that is exactly why Wednesday matters. Now, the paper's conclusion. This is where the language shifts, subtly, from describing an observing campaign to describing a problem. The event, they write, provides an opportunity to better understand the multimodal hazards posed to future lunar infrastructure and astronauts from space debris impacting the Moon. It also provides an opportunity to test our capability to monitor the cislunar environment. Read that second sentence again. Test our capability. They are not saying they will use their capability to monitor the space between Earth and the Moon. They are saying they will find out whether they have one, and then the line that should genuinely stop you. Given the renewed interest in lunar exploration, the impact of artificial bodies on the Moon is almost certain to become more frequent. To avoid uncontrolled increases in the amount of space debris in lunar orbit, as is the case now in low Earth orbit, advancing monitoring of cislunar space from ground and space-based facilities will be key. Notice what that concedes without ever quite saying it. They are comparing the future of the Moon to the present state of low Earth orbit. And low Earth orbit is the cautionary tale. It is the environment where the International Space Station has had to physically dodge debris dozens of times, where operators file collision avoidance maneuvers as routine paperwork, and where the long-term nightmare scenario has its own name. 23 scientists just wrote down, in a paper about a telescope schedule, that the Moon is heading in that direction, and that nobody is currently equipped to notice. There is a second paper, by the way. A separate group at the University of Texas at Austin submitted an ejector dynamics study to a major geophysics journal on the 24th of July, and they modelled something the first group did not. Where the Los Alamos team modelled the rocks, the Texas team modelled the dust, and they got numbers that sound completely different from the first papers. They are not different. They are the other end of the same distribution, and when you put the two together, you get the thing that actually threatens a moon base. But before we get there is a question you should be asking. The paper says 1,000 kilometres, and it says that number is a flaw. On what possible basis does a rock thrown out of a 27-metre hole travel 1,000 kilometres? The answer is that on the moon, that is not even difficult. Part 3. Why 1,000 kilometres is not an exaggeration. The moon has no atmosphere. You know that. Everybody knows that. But I think almost nobody has actually sat down and worked through what it removes, because we have never lived anywhere without one, and the absence is genuinely hard to picture. There is no drag. A moving object does not slow down. There is no terminal velocity because terminal velocity is the speed at which air resistance balances gravity, and with no air there is no balance point and no ceiling. There is no wind to disperse anything. There is no rain to wash anything down. There is nothing at all between the surface and the vacuum except the surface and the vacuum. So when a fragment of rock leaves the lunar surface at a given speed, it keeps that speed. Not approximately, exactly. Until something solid stops it, and the only solid thing available is the moon itself, somewhere else. Add the second fact. Lunar surface gravity is about 1.625 meters per second squared, roughly 1/6 of Earth's. It is weak, and weakness matters here, because gravity is the only thing that ever brings a fragment back down. Weak gravity plus no air is a specific and unusual combination, and it is the reason a local explosion on the moon becomes a distributed event across a continent's worth of terrain. Let us do the arithmetic out loud, because you can check it yourself and I would rather you did. The range of a projectile on a flat surface launched at the best possible angle is just its launch speed squared, divided by the gravity. That is it. That is the whole formula, and it has been in physics textbooks for 300 years. So, a fragment leaving the lunar surface at 100 meters per second travels about 6 kilometers before it lands. At 300 meters per second, it travels about 55 kilometers. At 600 meters per second, about 220 kilometers. And at 1200 meters per second, it travels about 886 kilometers. Now hold that last number against something from the paper. 1200 meters per second is precisely the maximum ejector velocity that standard impact scaling laws predict for Wednesday's collision. Run it through a formula a high school student could handle on a flat moon, and you get 886 kilometers. Correct for the fact that the moon is a sphere only 3,500 kilometers across, so the ground curves away beneath a fragment as it flies, and you get slightly more, slightly under 1,000. The number in the paper is not exotic, it is not a modelling artifact, it is not somebody being dramatic. It is what you get when you throw a rock hard on a world with no air, and it falls out of arithmetic so simple that the only reason it sounds shocking is that we have spent our entire existence somewhere with weather. Now, let me convert that range into an area, and I want to be clear that this next calculation is one I have done for this video. It is not a figure stated in the paper, so do not go quoting it as though the authors said it. Draw a circle on the surface of the moon with a radius of 1,000 kilometers centered on the impact. Because the moon is a sphere and that circle wraps around its curvature, the area inside it comes to roughly 3 million square kilometers. The moon's total surface area, the whole world, front and back, is about 38 million square kilometers, which means a single impact of this class can, in principle, place fragments anywhere within about 8% of the entire lunar surface. Counting only the side that faces us, it is about 16% of the near side. Try that in terrestrial terms. One explosion, capable of scattering debris anywhere across an area larger than the entire continental United States. And not as a plume, not as a cloud drifting on the wind, but as individual pieces of rock arriving on ballistic trajectories at hundreds of meters per second, with nothing slowing them down on the way in. At which point the natural question is whether any of it leaves entirely. The moon's escape velocity, the speed you need to break free of its gravity for good, is 2.38 kilometers per second, and the rocket stage is arriving at 2.43. So yes, the incoming object is, marginally, moving faster than the speed required to leave, but the ejecta is not, and this is where I have to correct the conclusion you might be tempted to draw, because getting this right matters more than making it sound impressive. The modelled maximum ejecta velocity is 1200 metres per second. Escape velocity is 2380. The fastest material coming out of that crater is moving at roughly half the speed it would need to leave, which means essentially every gram of material thrown out of that hole stays gravitationally bound to the moon. None of it escapes into space. None of it goes into orbit. All of it comes back down, and that is not the reassurance it sounds like. That is the problem. Think about what happens when something explodes on Earth. Debris goes up, air resistance robs it of energy almost immediately. It falls within a fairly small radius, and then the world begins erasing it. Rain moves it, wind buries it, plants grow through it, soil forms over it. Give it a few centuries and the ground closes over almost anything. The moon does none of that. There is no wind, there is no water, there are no plants, no soil chemistry, no plate tectonics recycling the crust, no erosion worth the name. The only process that modifies the lunar surface is more impacts. So everything thrown up on Wednesday morning comes back down somewhere else on the same surface, at speed, and then it stays exactly where it lands. Not for a long time, permanently. The footprints Neil Armstrong left in 1969 are still there, unchanged, sharp-edged, and they will still be there in 1,000,000 years. The craters gouged out by the Apollo upper stages deliberately crashed into the moon in the early 1970s to give the seismometers something to measure are still there. The pair of craters left by a Chinese rocket stage in 2022 are still there, and we have photographs of them. Everything we have ever done to that surface is still on that surface. The moon does not heal, it only accumulates. And I want to draw out one more consequence of the missing atmosphere, because it changes how you should think about every fireball story you have ever heard. When something hits the Earth, the atmosphere is not a minor factor, it is the main event. A rock coming in at 20 kilometres a second meets 100 kilometres of air, and that air is so unyielding at those speeds that it behaves less like gas and more like a wall. The rock heats, glows, fragments, and in the overwhelming majority of cases disintegrates completely before it ever reaches the ground. That is what a meteor is. It is not a rock landing. It is a rock being destroyed by air. Take the air away and none of that protection exists. Every single object that arrives at the moon, from a grain of dust to a rocket stage, arrives at full speed and hits the ground. Nothing burns up, nothing slows down, nothing is filtered out, and in the other direction, nothing that leaves the ground is slowed either. That asymmetry is why the moon is covered in craters and the Earth is not. It is not that the moon gets hit more often. Per square kilometre, over the history of the solar system, the Earth has taken a heavier beating than the moon has, because it is bigger and its gravity pulls in more. It is that the Earth has spent 4.5 billion years quietly erasing the evidence, with air and water and moving continents, and the moon has spent the same 4.5 billion years keeping a perfect and permanent record of every single thing that ever touched it. Which means that whatever happens on Wednesday morning becomes part of that record, forever. A 27-metre hole with our name on it, in a catalogue of impacts that goes back to the formation of the solar system, and it will still be legible when the sun begins to die. So here is the question that carries us into the next part of this. If one collision can throw material across 8% of a world, and none of that material will ever go away, then what exactly comes out of the ground when 4,000 kilograms hits it at 5,400 miles an hour? The answer is a number that I genuinely did not expect the first time I read it. Part 4. 1.1 million kilograms. Everything I am about to tell you came out of a computer. I want that stated plainly at the top of this section, because it is the honest frame and because it is the reason Wednesday morning matters at all. Nobody has ever measured what happens when a rocket stage hits the moon, not once. Every number in this part of the video is the output of a simulation that has never been checked against reality, and the entire point of the observing campaign is that on Wednesday, for the first time, somebody gets to check. The team ran the impact through what is called a finite discrete element code. In practice, that means they built a virtual block of lunar ground, divided it into millions of cells, gave those cells the physical properties of real regolith, and then fired a virtual rocket into it and watched what came out. They modelled the surface with a density of 1,590 kilograms per cubic metre, which is a standard figure for lunar soil, and set the resolution so that the smallest fragment the model could track was about 37 centimetres across. Then they added up how much material left the ground: 1,120,000 kilograms. An independent check using standard impact scaling laws derived from decades of laboratory experiments and observed craters gives 1,200,000. Two completely different methods agreeing to within 7%. Let me convert that into something you can picture. More than 1 million kilograms, over 1,000 tons, around 2.5 million pounds of lunar rock and dust and glass lifted off the surface of the moon and thrown into vacuum by one dead rocket that nobody has thought about since the spring of 2025. That is roughly the mass of 250 adult African elephants. It is a fully loaded freight train. It is a small office building, and it is going up in less than a second. But the number I actually want you to remember is not that one. It is the ratio underneath it, because the ratio is the part that generalizes to every future collision, and the paper flags it directly. The impactor excavates around 150 to 200 times its own mass. Sit with that, because it reframes the entire problem. When we talk about space junk, we instinctively think in terms of how much junk there is, how many objects, how many tons, how many pieces. But on the moon, the junk is not the hazard. The junk is the trigger. Every kilogram of hardware that hits the lunar surface converts itself into 150 to 200 kilograms of moving moon. So the hazard does not scale with how much we leave up there. It scales with roughly 200 times how much we leave up there. And the material doing the damage is not the rocket at all. It is the ground. Now, how that 1 million kilograms is distributed is where this gets genuinely interesting and where the physics stops being intuitive. The fragments follow what the paper calls a v to the -3 distribution. That sounds like jargon, and it is, but the meaning is simple, and it is worth having. If you double the speed, you get roughly 8 times fewer fragments moving that fast. Double it again, 8 times fewer again. So the overwhelming bulk of the material barely moves at all. It heaves up, arcs over, and comes down within a few tens of meters of the hole it came from. And then there is a thin tail on that distribution, a small population of pieces moving very much faster, and it is that tail that goes anywhere interesting. This is not a peculiarity of rockets. It is a general property of things breaking. Drop a wine glass on a stone floor and you'll find a few large pieces near your feet and a fine spray of tiny fragments across the entire room, and you will still be finding those a month later. Same distribution, same reason. The energy that goes into breaking material preferentially ends up in the smallest pieces, because they are the ones that need the least of it to move fast. Which brings us to the gap in the paper, and to their credit, the authors put it right there in the open rather than burying it. Scaling laws predict a maximum ejector velocity of 1,200 meters per second. That is the number that produces the 1,000-kilometer range we have been building toward. But at the end of the simulation's 9/10 of a second, the fastest particle the model could actually see was moving at only 130 meters per second, a factor of 9 between what the physics says should be there and what the computer could find. The authors explain it in one sentence, and the explanation is the whole story of this video in miniature. The model's smallest resolvable fragment is around 40 centimeters. In reality, they write, smaller fragments and entrained debris are expected to have much higher velocities. The fast material exists. Every laboratory experiment on impact cratering ever performed says it exists. The simulation simply could not see it, because it was built to be honest about big pieces rather than dishonest about small ones. And then there is the finding that I did not expect and have not seen reported anywhere. Approximately 50% of the particles the simulation could resolve come back down within 5 seconds. And the paper adds a short clause about what happens when they land. They will likely form secondary craters. Read that again. Half of the debris from this impact hits the ground hard enough and soon enough to dig its own craters. An impact that makes an impact field. Each of those secondary strikes throws its own material at lower energy over shorter distances, and each of those creates its own scatter. It is a cascade, and I want to be very careful about how far I push that word, because the honest version is less cinematic than the exciting one. It is a strongly damped cascade. Each generation carries dramatically less energy than the one before, so it dies out quickly rather than running away. This is not a lunar version of the runaway collision scenario that keeps orbital debris analysts awake at night. But it does mean that the footprint of this event is not one crater and a scatter of rocks. It is a crater, a field of smaller craters, and a scatter of rocks from every single one of them. And nobody has modelled the full secondary field for an artificial impact of this class, because until this week, nobody had a reason to. The flight times tell you how it unfolds in real time. Half the resolved material is down within 5 seconds. Only 2% is still airborne after 30 seconds. The longest-lived resolved particles stay up for a couple of minutes, and the smaller, faster fragments, the ones the model could not follow, are expected to remain aloft for something on the order of 10 minutes. 10 minutes is a long time for a rock to be in flight above a world where you can see the horizon curve away. Which brings us back to that second paper, the one from Texas, and to the disagreement that turns out not to be a disagreement at all. The Los Alamos-led team, modelling the pieces bigger than 37 centimetres, found that the material reaches about 1.5 kilometres in altitude. The Texas team, modelling the fine dust, predicts an ejector curtain reaching 15 to 20 kilometres, a central spike shooting up to somewhere between 75 and 100 kilometres, and the whole structure spreading roughly 183 kilometres sideways across the lunar surface. 1.5 kilometres, or 100 kilometres, that is a factor of nearly 70 between two papers about the same collision, published 8 days apart. And both are correct. The first paper is describing the rocks. The second is describing the dust. They are two ends of the same distribution, and the reason the numbers look irreconcilable is that they are answers to two different questions that were never clearly separated in any of the coverage. Now hold those two pictures together, because this is the thing that actually matters for anybody who ever intends to live on the moon. The big rocks stay low and land close. That is a hazard you can design around. You keep your habitat away from where rockets come down, you put a berm around it, you accept the residual risk, and you get on with your life. The fine dust goes up 100 kilometres and travels for hundreds more. And fine dust does not care about berms. Fine dust does not care about walls. Fine dust gets into the hinge of an airlock, into the bearing of a rover wheel, onto the surface of a radiator that has to shed heat, or the crew cooks, onto a solar panel that has to stay clean, or the power budget collapses, and onto the visor of a helmet that has to stay transparent, or somebody dies out there because they could not see where they were putting their feet. The rocks are the headline, the dust is the problem. So we have 1 million kilograms of lunar material in flight, a plume potentially reaching 100 kilometres above the surface, and a debris field measured in hundreds of kilometres across. By any reasonable expectation, this should be one of the most spectacular things any human being has ever watched happen to the moon. The scientists organising the observing campaign think you will probably see nothing at all. Part 5. The flash you will probably never see. 14.5 billion joules. That is the energy this thing arrives with, using the higher of the two mass estimates, roughly 3 tons of TNT, roughly the energy contained in 15,000 sticks of dynamite, all released in a fraction of a second, in a vacuum, with nothing to muffle it, absorb it, or spread it out. And the working assumption of the people who have spent their careers studying lunar impact flashes is that the Earth will register nothing. There are 2 reasons, and the first one is obvious. The impact is on the sunlit half of the moon. You're trying to see a brief spark against a surface that is currently being blasted by unfiltered sunlight and is one of the brightest objects in the night sky. It is the same problem as trying to spot a match struck in a stadium at noon. The paper states it flatly. There has never been a natural or artificial impact flash detected on the lit portion of the lunar surface. Not once. Every lunar impact flash ever recorded, several hundred of them since 1999, has been caught on the dark part of the disk. The second reason is much more interesting, and I have not seen it explained properly anywhere, which is a shame because it is the kind of thing that rearranges how you think about impacts. The object is going too slowly. That sounds backwards. More speed means more energy. More energy means a bigger bang. A bigger bang means a brighter flash. But that is not how impact luminosity works, and the reason has to do with sound. Whether an impact produces a bright flash depends on whether the impactor drives a shockwave into the ground. And you only get a shockwave if the object is travelling faster than the speed of sound in the material it is hitting. Below that threshold, the material has time to get out of the way. It deforms, it compresses, it flows. Above that threshold it cannot. The information that something is coming cannot propagate ahead of the thing itself, so the material is violently compressed with no warning, and that violent compression is what dumps energy into heat and light. Now, the speed of sound in loose lunar regolith is a few hundred meters per second. It is dust and broken rock sitting on more dust and broken rock, and sound moves through it sluggishly. But the speed of sound in solid lunar bedrock is between 1,000 and 2,000 meters per second. The rocket stage arrives at 2,430 meters per second. So if it comes down on loose regolith, it is comfortably supersonic in that material. Shockwave, flash, the whole show. If it comes down on exposed bedrock, it is barely above the sound speed, or in the wrong part of the range entirely, and the flash essentially does not happen. And the impact ellipse, the region where we know it will land, contains both, which produces the widest prediction I think I have ever seen in a scientific paper. Expected brightness runs from magnitude +3 at the optimistic end, which would make it comparable to the brightest natural lunar impact flashes ever recorded and visible to a modest telescope, all the way down to fainter than magnitude 15 at the pessimistic end. Magnitude 15 is invisible to essentially every instrument that will be watching. The gap between those two predictions is a factor of more than 10,000 in brightness. Bill Cook, who runs NASA's Meteoroid Environment Office, made the same point in plainer language. Natural rocks hitting the moon are typically moving at around 10 kilometres per second and can arrive at up to 70. The faster the impact, the greater the fraction of the energy that comes out as visible light. This object will release an enormous amount of energy and almost none of it as light. Benjamin Fernando, the lead author, put the practical odds like this. The flash, he said, is going to be tough because it is on the lit side of the moon and it is very short-lived, but that does not mean people should not try. He also gave the technical advice, which is genuinely useful if you own a telescope and a camera. To have any chance at the flash, you need to be taking an image every 10th of a second or every 100th. The event may last under 1 second. If you are shooting at ordinary video rates, you can miss it entirely in the gap between frames. The plume, he said, is a much easier target because the plume is expected to last on the order of 1 to 10 minutes. There is a precedent that explains why everybody involved is bracing for disappointment, and it is worth telling properly. In 2009, NASA deliberately crashed a spent Centaur upper stage into the moon. The mission was called L-Cross. The stage weighed 2,305 kilograms and hit at about 2.5 kilometers per second, which is almost exactly the profile of Wednesday's impact. And unlike Wednesday, every single variable was chosen to make the event observable. They picked the target, they picked the timing, they aimed it at Cabeus crater in the permanently shadowed region near the lunar south pole, on the dark side of the terminator precisely so that a flash would stand out. They arranged for large telescopes to be watching. They even sent a second spacecraft in behind it to fly through the plume and take measurements on the way down. Earth-based telescopes saw nothing at the moment of impact. The flash, as it turned out, was blocked from our line of sight by a small hill. Evidence of the plume was eventually teased out of archival data years later, at an optical depth of about 0.0018, which is to say almost perfectly transparent. The mission did succeed at its actual scientific goal. It measured roughly 5.6% water ice in the material it kicked up, which was a genuinely important result, and it left behind a crater 22 meters across, with an estimated 350 tons of excavated material. But the headline lesson, for our purposes, is that the last time humanity deliberately threw a rocket stage at the moon, under ideal, hand-picked, fully instrumented conditions, we could not see it happen. And here is the fact that I think should genuinely stop you, because it did stop me. In 67 years of hitting the moon, we have never once measured how bright it is. The first artificial object to hit the lunar surface was Lunar 2 in 1959. In 1963, it was reported that Soviet astronomers had observed the flash from that impact. That report has never been confirmed with images or with any other evidence. Japan's Hiten spacecraft hit the moon in 1993, and the flash was captured by a telescope in Australia. Europe's Smart 1 hit in 2006, and that flash was resolved by a 4-meter class telescope in Hawaii. In both of those cases, the magnitude was never robustly determined, so we have crashed probes, landers, upper stages and entire spacecraft into that surface, deliberately and accidentally, for 2/3 of a century. And there does not exist anywhere in the published literature a single measured brightness value for an artificial lunar impact. That is what Wednesday is actually for. Which is why the campaign is as serious as it is. Time has been allocated on the 3.5-meter telescope at Apache Point Observatory in New Mexico for high-cadence imaging. The 4.3-metre Lowell Discovery Telescope will be running spectroscopy looking for sodium, and one of the 8-metre units of the Very Large Telescope in Chile will be watching with an instrument capable of picking out hydroxyl, sodium and potassium emissions from the plume gases. Amateur coordination is running through a NASA-affiliated citizen science project and a European Lunar Impact Flash network. The guidance to amateurs is 20 frames per second or better, and apertures as small as 4 inches are explicitly welcomed, because in past campaigns small telescopes have contributed real detections. And then there is the strangest recommendation in the whole document, which I have been waiting to tell you about. Observers are being encouraged to try a very narrow filter at 670.8 nanometers. That is the lithium line. Lithium has a strong accessible emission doublet at that wavelength, and Falcon 9 upper stages have been observed releasing detectable lithium when they burn up in Earth's atmosphere, almost certainly from aluminium-lithium alloy in the tank structure. So there is a real chance that when this thing hits, the plume will glow with a chemical signature that belongs to the rocket rather than to the moon. I find that detail quietly remarkable, and not for the reason the paper cares about. The scientists are interested because it gives them a clean spectral fingerprint to look for. But step back from the instrument and look at what is actually being described. We are discussing how to identify our own hardware by the light of the metals it is depositing on another world. At current scale, that is completely negligible. A few kilograms of alloy on a body with a surface area of 38 million square kilometres is nothing, and I'm not going to pretend otherwise. But nobody has established at what scale it stops being nothing, because nobody has been asked to. The flash may be invisible, the plume may be invisible. But there is one thing this impact is guaranteed to leave behind, and a spacecraft is already scheduled to go and photograph it. Part 6. The crater, and the one that should not exist. Whatever happens in the sky above Einstein crater on Wednesday morning lasts minutes at the outside. What happens to the ground lasts geological time. The paper expects a final crater diameter of 20 to 30 metres. Standard scaling, using a method derived from decades of laboratory impacts and calibrated against real craters, gives 27 metres across and about 5 metres deep. Benjamin Fernando has put it in plainer terms for general audiences, roughly 90 feet wide and 16 feet deep. Bill Gray, working independently and scaling from the craters left by the last rocket stage to hit the moon, gets a smaller number, about 17 metres, with a guessed average depth of around 2 metres. The two estimates differ because they assume different things about how deep the excavation goes and how dense the material is, not because either party has made an error. When you see a range like that in a story like this, the range is the honest answer. Anyone quoting you a single confident figure is quoting you somebody's assumption. There is a third number in the paper that matters more than either of those, and it gets almost no attention. Modelling suggests the ejector blanket, the continuous layer of material thrown out and laid back down around the hole, will cover an area roughly 70 metres across. 70 metres of freshly excavated lunar material, exposed at the surface for the first time in what may be billions of years. And here I want to be fair to the science, because this video is not an argument that the impact is bad. That fresh material is a genuine scientific gift. It is subsurface composition, brought up and laid out where an orbiting spacecraft can photograph and analyse it, without anyone having to fund a drilling mission to get at it. The paper says so directly. It presents a large target region in which fresh material will be excavated and may be imaged by subsequent spacecraft flyovers, and this will be particularly advantageous for understanding the composition of the target material. We are going to learn things from this. That is true, and it deserves saying. But there is a warning buried in the same section, one short clause that opens up the strangest unresolved story in this entire field. A double crater may be produced, the paper says, if the impactor is decapitated. Decapitated, meaning the rocket stage does not arrive as a single object. It breaks apart in the moment of impact, and two separate concentrations of mass strike the ground separately, in two separate places producing two separate holes. Why would anyone write that sentence about a 12-metre cylinder? Because it has happened before, and nobody can explain it. On the 4th of March, 2022, another abandoned rocket stage hit the far side of the moon. It was the first junk impact ever predicted in advance, and it was predicted by the same astronomer who predicted this one. Because it happened on the far side, nobody saw it. There is no flash observation, no plume observation, no timing measurement. It simply happened, out of sight, and the only way to know anything about it was to send a spacecraft to look at the aftermath. Roughly 3 months later, the Lunar Reconnaissance Orbiter photographed the site. It did not find one crater, it found two, one about 16 meters across, one about 18, roughly 30 meters from end to end. Two clean, distinct, overlapping holes from one rocket. Nobody has explained it. The current best guess, and Gray is careful to label it as a guess, is that there was a heavy engine at one end of the stage and some additional heavy mass near the top, and that the two ends came apart and hit separately. His own words on the matter are that we do not really know. And then there is the part that turns a technical anomaly into a story. That object was identified as the upper stage of a Chinese lunar mission launched in 2014. The identification was made from orbital tracking, and it was later supported by spectroscopic work matching the reflected light from the object's paint to other Chinese upper stages. The China National Space Administration has never publicly acknowledged that the object was theirs. Not denied, exactly. Just never confirmed, 4 years and counting, about a piece of hardware that made 2 permanent craters on the moon. Now, I want to deal with something head-on, because it is the strongest argument anybody could make against everything in this video, and I would rather raise it myself than have it raised at me. When that 2022 object was first spotted, Bill Gray identified it as a Falcon 9 upper stage from a launch in 2015. He was wrong. It was not a Falcon 9. It was Chinese. And here is what he did about it. He posted the correction on his own website under his own name, without anybody forcing him to, explaining exactly what he'd got wrong and how. He has done the same thing since with a piece of arithmetic on the same page, when a reader of an astronomy magazine caught him squaring a number once instead of twice. Both corrections are still there, dated, with the reader credited. That is what makes the current identification trustworthy, rather than what makes it suspect. This is a man with a documented public habit of announcing his own errors, and the current identification is on far firmer ground than the 2022 one ever was. All 4 objects from the January 2025 launch were tracked continuously, from the launch pad onward. There is no gap in the chain of custody. By late February of this year, there were 1,053 separate observations of this specific object, gathered from 5 observatories spread across Mississippi, Utah, Beijing, and England. 3 continents, independent observers, all fitting the same orbital solution. The genuinely unresolved scandal from 2022 is not the misidentification. That got fixed, in public, by the man who made it. The unresolved scandal is that a national space agency put an object on a collision course with the moon. It made 2 craters nobody predicted, and 4 years later, that agency has still not said a word. So what happens after Wednesday? The Lunar Reconnaissance Orbiter has already acquired baseline imagery of the impact site. It will photograph it again afterward. And because the impact point is now predicted to within a few kilometres, and will be predicted to within a few hundred metres by the time it happens, the team expects to be able to tell the orbiter's operators almost exactly where in their images to look. If they find a single crater somewhere in the 17 to 30 metre range, the models are validated. The scaling laws work. The ejector predictions gain credibility, including the 1,000-kilometre one, and everyone goes home reasonably satisfied. If they find 2 craters, the 2022 question reopens completely. And it would mean that both times in history that humanity has watched a rocket hit the moon, it produced a crater that nobody correctly predicted, which would be a difficult thing to reconcile with the confidence of anyone claiming to know what happens when the next one lands somewhere that matters. And that assumption, that any of this only matters because we are curious, is the one I want to take apart next. Because there is one place on the moon where we already know exactly what happens when something lands too close to something else. We ran that experiment by accident in 1969, and the evidence has been sitting in a laboratory ever since. Part 7. What Apollo 12 did to Surveyor 3. We are not speculating about what lofted lunar material does to hardware. That is the thing I want you to take away from the next few minutes, because so far everything in this video has been a model, a simulation, a scaling law, a prediction that will not be tested until Wednesday morning, and might not be tested even then. This part is not a model. This part is an experiment that was already run on the moon with real hardware, and the results have been sitting under a microscope in a laboratory for over half a century. Start in April 1967. An uncrewed American probe called Surveyor 3 soft lands in Oceanus Procularum, the ocean of storms. It is a spindly three-legged thing with a television camera and a small scoop on an extending arm, and its job is to find out whether the lunar surface is solid enough to land people on, because at that point nobody was entirely sure it was. There was a real, seriously argued theory in the 1960s that the moon might be covered in a layer of fine dust deep enough to swallow a spacecraft whole. Surveyor 3 does its job. It digs, it photographs, it proves the ground will hold. And then its batteries die, and it stops, and it sits there in vacuum, motionless, for the next 2.5 years, being slowly cooked by 2-week-long days of unfiltered sunlight, frozen through 2-week-long nights, and pitted continuously by micrometeorites too small to see. Then, in November 1969, Apollo 12 comes down. Pete Conrad and Alan Bean bring the lunar module Intrepid to a landing roughly 155 to 160 metres from where Surveyor 3 is sitting. This was deliberate. It was a precision landing demonstration, and it worked, and it remains one of the more underrated pieces of flying in the entire programme. And because they were close enough to walk, they walked. They photographed it, they inspected it, and then, with a pair of cutters, they removed pieces of it and brought those pieces home. Now, the reason they did that was to study long-duration exposure. Nobody had ever had a sample of hardware that had sat on the lunar surface for years, and engineers desperately wanted to know how materials aged out there before committing to anything long-term. That was the stated scientific purpose. What they got, accidentally, was the only physical record in existence of what a landing does to a neighbour. The samples came back covered in sandblasting damage, not dirt, not discoloration, damage. Regolith lofted by Intrepid's descent engine had struck the exposed surfaces of Surveyor 3 hard enough to excavate material out of them. Here are the numbers, and I want to go through them slowly because they are the most concrete thing in this entire story. Coupon samples from the probe showed on the order of 103 pits per square centimetre. The mean pit dimensions were roughly 84 by 75 micrometres, at depths of around 89 micrometres. Let me translate that because micrometers mean nothing to most people, and the translation is what makes this land. A square centimetre is smaller than a fingernail. In that space there were around 100 individual impact craters, each one somewhere between 1/12 and 1/10 of a millimetre across, and about as deep as it was wide, punched into painted metal and glass by grains of lunar soil moving fast enough to dig. 100 craters in a fingernail-sized patch, across the entire exposed surface of the spacecraft, from a landing that happened 155 metres away. Reconstruct the geometry for a second, because that distance is the part people skip over. 155 metres is a football pitch and a half. It is a long city block. On Earth, if a helicopter lands a block and a half from where you're standing, you turn your back and squint and wait for the dust to settle, and then you carry on with your day, and nothing about your surroundings is permanently altered. On the Moon, the same separation left a permanent microscopic crater field carved across every exposed surface of a spacecraft, which is still measurable today, and which will still be there in 100 million years. That is the difference between a world with air and a world without one, expressed as physical damage rather than as a formula. And the crews knew something was happening even as it happened, because they could see it from the window. The Apollo landing reports describe something that surprised everybody the first time it was observed. As the lunar module came down through the last 30 metres or so, the dust did not rise up around the vehicle the way it does around a helicopter. It shot outward, almost horizontally, in a thin sheet that raced away across the surface, faster than the eye could follow, and it did not settle afterward because there was nothing to settle through. Crews described the ground below them essentially disappearing in the final seconds of descent, replaced by a fast-moving haze that gave no depth cues at all. Pete Conrad, coming down on Apollo 12, was flying largely on instruments and the feel of the vehicle in the last moments, because what he could see out of the window had stopped being useful. That is what a 15-ton vehicle does. And every crew that ever did it reported the same phenomenon, because it is not a quirk of any particular lander. It is what an engine plume does when there is no air to make it behave the way our instincts expect. Now here is what NASA did about it, and this is the part that matters most for our argument. In 2011, the agency issued guidance recommending that small lunar landers should not touch down within 2 kilometres of the Apollo landing sites, specifically to protect those sites from dust. 2 kilometres. That is the officially recommended separation between a controlled, deliberate, low-energy landing and something you would rather not sandblast. The modelled ballistic range from Wednesday's uncontrolled impact is 1,000 kilometres. That is 500 times further. And I have to immediately qualify that comparison, because if I let it stand unqualified, it would be exactly the kind of dishonest number stacking this channel is supposed to avoid. A landing plume and an impact ejector field are genuinely different physical events. A descent engine produces a dense, sustained, low-altitude sheet of material blowing sideways for tens of seconds. An impact produces a violent, instantaneous upward and outward spray with a completely different particle population and a completely different energy distribution. The 2-kilometre figure is about a dense sheet close to the ground. The 1,000-kilometre figure is about the fastest 1% of the tail of a ballistic distribution, and the overwhelming majority of the material never gets anywhere near that far. You cannot simply divide one by the other and announce that lunar impacts are 500 times worse than landings. They are not the same quantity. But here is why the comparison still stands and why I brought you here. Both numbers are measurements of the same underlying property of this world. Material moved on the moon does not stop where it would stop on Earth. It goes much, much further because there is nothing to stop it, and we have already acknowledged that formally. We have already written it into guidance. We have already decided, as a species, that there are places on the moon worth protecting from our own hardware, and we wrote down a number. We just wrote down the smallest possible version of that number for the smallest possible version of the problem. And there is one more thing about that 2011 guidance that you should know, and that almost nobody mentions when it gets cited. It is non-binding. It is a recommendation, a suggestion, a piece of advice issued by one national space agency to whoever happens to be listening. There is no lunar authority with the power to require anyone to follow it. There is no penalty for ignoring it. There is no permit that gets denied, no license that gets pulled, no court with jurisdiction. If a private company or a national program decides to land 800 meters from Tranquility Base tomorrow, the entire enforcement mechanism available to the rest of humanity is a strongly worded press release. Think about what that means as a statement of where we are. We have understood the physics since 1969. We have had the damaged hardware in our hands since 1969. We wrote a protective rule in 2011, and we never gave anyone the power to enforce it, and we never extended it to cover anything except 6 specific historical sites. Nothing protects a future base. Nothing protects a future landing site. Nothing protects the polar ice deposits that everybody is racing toward. There is a 2-kilometre suggestion about Apollo, and beyond that there is nothing at all, and the hardware is getting bigger. Surveyor 3 was pitted by a lunar module that weighed about 15 tons fully loaded on descent. The landers being built now, the ones intended to put people back on that surface and keep them there, are an order of magnitude heavier than that. Which brings me to the number that reframes everything you have just heard, because the 1,000-kilometre figure in Wednesday's paper is not some strange new claim about a bizarre one-off event. It is the same physical property of this world that pitted Surveyor 3, finally measured at the scale of a full impact instead of a landing. The moon has always behaved this way. We just never had a reason to put a number on it before because there was never anything up there worth hitting. Part 8. The sheet of glass moving at 2 kilometres, a second. I want to correct the mental image you're almost certainly carrying because I carried it too for years. When you picture a spacecraft landing on the moon, you probably picture the engine kicking up a cloud of dust that billows outward and then slowly settles. That is what happens on Earth. It is what happens in every piece of film you have ever seen of a helicopter landing in a desert. It is not what happens on the moon because a cloud requires air. Without air, there is nothing for the dust to billow into, nothing to make it swirl, nothing to hold it up and let it drift and settle gently. The exhaust does not make a cloud. It strips the surface and throws it sideways in a nearly flat, nearly invisible sheet travelling outward almost parallel to the ground, at speeds that have no terrestrial equivalent at all. Here is that sheet, broken down by particle size from the lunar surface engineering literature. Fist-sized cobbles come off at around 10 meters per second. That is a stone thrown hard by a person. Gravel moves at around 30 meters per second, roughly highway speed. Sand-sized grains travel at somewhere between 100 and 1,000 meters per second. which at the upper end is faster than most rifle bullets, and the finest material, the dust, reaches speeds in the range of 1.5 to 2 kilometers per second. Now compare that to the number we established earlier. Lunar escape velocity is 2.38 kilometers per second. The finest material kicked up by a rocket landing on the moon is moving at up to 2 kilometers per second. It is not quite escaping. It is going most of the way to escaping, and then, gravity being what it is, coming back down somewhere very, very far away. A single landing does that. Not an impact, not a crash, a successful, nominal, textbook landing, and there is a consequence to this that almost nobody outside the field is aware of, which I find genuinely astonishing given that it applies to hardware currently being built. Researchers modelling a roughly 40-ton class lander, the size of vehicle now being developed to carry people, calculated what happens to spacecraft that fly through that ejector sheet from above. For the Lunar Gateway, the station intended to orbit the moon in a wide, high, elongated path. The modelling gives thousands to tens of thousands of particle impacts per square metre every time it passes through the sheet, and then the reassuring half of the finding, which deserves as much airtime as the alarming half. The particles that make it to that altitude are tiny, around 10 micrometers across, and gravity has been decelerating them the entire way up, so they arrive at only a few hundred meters per second. The modelled damage is described as slight. Gateway, in other words, is probably fine, but a spacecraft in a low lunar orbit close to the surface, passing through the same sheet, is not fine. The modelling gives hundreds of millions of impacts per square metre, not thousands, hundreds of millions. And down there the particles have not had time to decelerate, so they arrive in what engineers call the hypervelocity regime, which is a polite way of saying fast enough that the material behaves like a fluid on contact. The modelled result includes spallation, the flaking away of surface layers, across roughly 4% of exposed glass surfaces. 4% of exposed glass does not sound like much until you think about what glass does on a spacecraft. Camera windows, radiator coatings, solar cell covers, star trackers, the instruments that look at the sky and tell the spacecraft which way it is pointing, optical sensors that have to see clearly or the vehicle cannot navigate. Every one of those surfaces has to stay transparent to work at all, and 4% surface damage on an optical component is not a cosmetic problem, it is a degraded instrument. So the picture is this. Every time a large vehicle lands on the moon, it fires a sheet of high-velocity debris outward across the surface and up into orbit, and anything in a low orbit that happens to pass through it takes measurable damage. That is a consequence of landing, of doing the thing correctly. And the people who study this are not sitting on their hands about it, which is worth saying, because the story so far has been relentlessly bleak, and the engineering community is genuinely ahead of the policy community here. There is an active research field devoted entirely to what is called plume-surface interaction, and the proposed fixes are inventive. One approach is to build landing pads, sintering the regolith into a solid surface, using concentrated sunlight or microwaves so there is nothing loose left to throw. Another is to construct berms, physical walls of piled soil around a landing zone, to intercept the sheet before it leaves the area. A more elegant proposal published this year suggests using the moon's own geography, landing inside existing craters so that the crater rim itself acts as the barrier and the ejector sheet slams into a wall that has been standing there for 3 billion years. All of those are real, and several of them will probably be built. But notice what every single one of them has in common. They are all mitigations for landings, for events we control, at sites we choose, with vehicles we designed. Not one of them does anything whatsoever about a 4,000-kilogram rocket body arriving unannounced at 5,000 miles an hour at a set of coordinates that nobody selected. You cannot build a berm around the whole moon. Now let us talk about the material itself, because I have been calling it dust and that word is doing it a disservice. Lunar regolith has never been weathered. On Earth, every grain of sand you've ever touched has been tumbled by water or blown by wind for thousands or millions of years, and those processes round the edges off. Sand feels the way it feels because the world has polished it. Nothing has ever polished the moon. Lunar soil is made by micrometeorites hitting rock at tens of kilometers per second, melting a little of it and shattering the rest. What that produces is angular, fractured, and glass sharp. Under a microscope it looks less like sand and more like a field of tiny broken bottles and splinters. It has been described by people who have handled it as feeling like fine powder and behaving like ground glass, and both of those things are true simultaneously. It also holds an electrostatic charge, because it sits in unshielded sunlight and solar wind with no atmosphere to bleed the charge away. So it does not just sit where it lands, it clings to fabric, to metal, to visors, to itself. The Apollo crews found this out the hard way, and the medical record is unambiguous. Every single one of the 12 people who walked on the moon reacted to the dust. Harrison Schmitt, the geologist who flew on Apollo 17 and is the only trained scientist ever to have stood on that surface, gave the condition its name: lunar hay fever. Sneezing, nasal congestion, irritation of the eyes and throat, beginning as soon as the dust that had been tracked back inside on the suits was released into the cabin atmosphere. In some cases, the symptoms took days to fade, and that was from a few hours outside. 3 days on the surface at most. The equipment fared no better. The dust abraded seals. It got into bearings and joints and degraded their motion. It coated thermal control surfaces, which are designed to radiate heat away and cannot do it through a layer of insulating powder. It settled on solar panels and cut their output. It scratched visors. Apollo suits came back with visible wear on their outermost fabric after surface excursions measured in hours, not months. The wrist and knee joints on some suits were reportedly close to failure after 3 days of use. 3 days. Now, I want to be careful and honest about where the science currently stands on the health question, because it is genuinely unsettled, and it would be easy to pick whichever study suits the argument. Recent work is split. A 2025 study found that lunar dust induces minimal pulmonary toxicity when compared against common terrestrial dusts, which is a real and reassuring result and should be reported as such. Other work continues to raise concerns about chronic exposure, and about the purely mechanical irritancy of particles that sharp, and about what happens when dust that has settled inside a habitat is stirred back into the air and breathed again and again over months. The honest summary is this: short Apollo exposures produced mild, short-lived symptoms. Long-duration, repeated exposure has never been characterized in a human being, because no human being has ever been there long enough for anyone to find out. And look at the shape of that gap. The exposure regime nobody has data on is precisely the exposure regime that a permanent base creates. We know what 3 days does. We have no idea what 3 years does, and the entire point of everything currently being built is to make 3 years the normal case. So bring the two halves of this act together. An impact of the kind happening on Wednesday throws over 1 million kilograms of this material off the surface and scatters it across hundreds of kilometres, and the part that travels furthest is not the rocks. It is the fine fraction, the fastest, smallest, most numerous particles, the ones the simulation could not even see, which is to say the part of the debris field that travels furthest is exactly the same material that gets into seals and joints and lungs and never comes out again. The rocks are what you would design a wall against. The dust is what goes over it, around it, through the airlock into the machinery and stays. So if the physics has been understood since 1969, and the hardware damage has been sitting in a laboratory since 1969, and 23 scientists have now put a 1,000-kilometre hazard range in print, then why is a rocket allowed to hit the moon on Wednesday at all? The answer is not that somebody weighed the risk and decided it was acceptable. Part 9. 25.6 billion times fainter. There is an assumption almost everybody carries about space, and it is so reasonable that I held it myself until I started reading about this properly. The assumption is that somebody, somewhere, is keeping track, that there is a room with screens in it, in a building with a fence around it, where every object humanity has put into space is a dot on a display, tracked, catalogued, and watched. That when a piece of debris is heading somewhere it should not be, an alarm goes off and a person in a uniform picks up a phone. For low Earth orbit, that assumption is broadly correct, and it is genuinely impressive. The United States military maintains a catalogue of tens of thousands of objects in orbit around the Earth, tracked primarily by radar, updated continuously. The resolution of that system is remarkable. Over the decades, it has tracked gloves and tool bags that astronauts have dropped during spacewalks. A glove, moving at 8 kilometers a second, 400 kilometers up, and the system knows where it is. Now let me take that away from you. The moon is about 400 times further away than low Earth orbit, and radar does not degrade gracefully with distance. It degrades catastrophically because the signal has to make the trip twice, walk it through. A radar transmitter sends out a pulse, and that pulse spreads as it travels, so the energy that actually reaches the target falls off with the square of the distance. 400 times further away means the object receives 1 over 400 squared of the energy. That is 1/160,000th. Then the object reflects some of that energy back, and the reflection spreads out on the return trip in exactly the same way. So of the tiny fraction that arrived, only 1/160,000th of it makes it back to the receiver. Multiply those together, and you get the inverse fourth power law, and you get a number that ends the conversation. The radar signal returning from an object at lunar distance is about 25.6 billion times fainter than from the same object in low Earth orbit. Radar does not work out there. Not poorly. At all. The entire architecture that tracks gloves and tool bags around the Earth is functionally blind past a certain distance, and the Moon is very comfortably past it. There is a small detail attached to that figure which I want to include, because it says something important about the quality of the source. When Bill Gray first published that calculation on his page, he got it wrong. He squared 400 once instead of twice, and was off by a factor of 100. A reader who had seen the story in an astronomy magazine wrote in and corrected him. He fixed it, dated the change, listed it publicly in a running log of corrections on the same page, and credited the person who caught it by name. I am telling you that because in a story about institutional failure, it is worth being clear about who is behaving well. The individual doing this work is scrupulous. The system around him is the problem. So if radar cannot see cislunar objects, who does? Asteroid surveys. Telescopes built and funded for an entirely different purpose, which is to find rocks that might hit the Earth. And they see this material completely by accident. The reasoning is simple and slightly absurd. An asteroid survey works by taking repeated wide-field images of the sky and looking for points of light that move slightly between frames. That is what an asteroid looks like from here. It is also, exactly and unavoidably, what a piece of high-altitude space junk looks like from here. Both are slowly moving points of light. There is no filter that separates them at the moment of detection. Gray puts it plainly. From the viewpoint of the asteroid observers, time spent observing junk is time not spent finding rocks. But both the rocks and the high-altitude space junk are slowly moving points of light in their images, and they are not easy to distinguish. So the surveys find this sort of junk whether they want to or not. Read that as a resource allocation problem, because that is what it is. Every hour a planetary defense survey spends chasing down a dead rocket body, confirming what it is, and clearing it from the queue, is an hour not spent looking for something that could actually hit us. The programs built to protect the Earth from asteroids are being partially consumed as an unfunded side effect by cleaning up after our own launches. Nobody planned that. Nobody budgeted for it. It just happens, quietly, every clear night. And now consider the human scale of the system that produced Wednesday's prediction. One man, working under contract, who has written publicly that he is never quite sure whether to describe himself as an amateur or a professional, because he has made his living as an astronomer for decades but does not hold a doctorate, and in some circles that word requires one. He has now predicted both of the only 2 junk impacts on the Moon that have ever been predicted in advance. Not one of 2. Both of them. The entire historical record of humanity anticipating one of its own objects hitting the Moon consists of 2 events, and the same person called both. Reconstruct how he did it, because the process is not what most people would imagine. In September 2025, his orbit determination software, chewing through observations gathered from asteroid surveys and amateur astronomers, flagged that this object was going to hit the Moon on the 5th of August 2026. 11 months of warning from a piece of software he wrote himself. By late February of this year, there were 1,053 observations of the object in hand. As the date approached and he wanted the impact point pinned down more tightly, he did not file a request with an agency. He posted a message to the Minor Planet mailing list, asking whether anybody could get more data on it. Amateur astronomers around the world pointed their telescopes at a dead rocket and sent him the results, and the prediction got better. That is the system, a mailing list. The reason he needed the extra data at all is a piece of physics that I think is genuinely beautiful, in an unsettling way. Gravity is not the uncertainty here. We know the gravitational fields of the Earth, the Moon, the Sun, and the planets with extraordinary precision. Gray has said that if gravity were the only force acting on this object, he could tell you where and when it would hit the Moon, to within a few meters and a fraction of a second, 11 months out. The problem is sunlight. Photons carry momentum. When they strike a surface, they push. It is an unbelievably gentle push, far too small to notice on anything with real mass over any short period. But this object has been drifting in sunlight for 18 months, and over 18 months an unbelievably gentle push adds up to something that matters. Worse, it is not a constant push. The stage is tumbling. As it rotates, it presents different faces to the sun, catches different amounts of light, and reflects some of that light sideways rather than straight back. So the force is mostly directed away from the sun, but with a small, wandering, unpredictable sideways component that depends on exactly how the object is spinning at any given moment. Sunlight is nudging a 5-story building around in space, and that nudge is the largest source of error in the entire prediction. You can watch it in the update history. On the 8th of June, new data moved the predicted impact 9 minutes earlier and 170 kilometres to the northwest, 170 kilometres from sunlight. On the 17th of July, another update moved it by about 2 seconds and 10 kilometres. On the 1st of August, another refinement. The formal precision of the current solution is about half a second in time and 1/100th of a degree in position, which is roughly 300 metres. Gray does not believe it. He says so explicitly. He does not trust it better than a few seconds and a few kilometres, because the theory does not handle the unpredictable part well, and no amount of arithmetic will make it. Meanwhile, amateurs have been characterising how the thing tumbles. An observer in the United Kingdom named Grant Privet took a 12-minute exposure in which you can watch the object brighten and fade 5 separate times as it rotates. Another observer, Jean-François Gu, produced a light curve showing the rise and fall in brightness over a little more than 3 minutes. Volunteers working out the rotation rate of a derelict rocket, because that rotation rate feeds back into how sunlight is pushing it, which feeds back into where it will land. Nobody is paying them. Nobody assigned them. They are doing it because it is interesting and because they noticed nobody else was going to. And then there is the detail I have been saving for the end of this section, because it does more work than anything else in it. Approximately 2 minutes before impact, this object will pass within a few kilometres or less of the Korea Pathfinder lunar orbiter. That is a functioning national spacecraft. It belongs to a space agency. It cost money, it has a mission, it has an operations team, and it is currently doing science in orbit around the moon. I want to be precise here, because it would be very easy and very cheap to call this a near miss, and it is not one, in any formal sense. The conjunction is computed, it is known, it is published in the paper in a plain sentence as a fact about the geometry. Nobody involved is alarmed by it, and nobody should be. But hold the whole picture in your head for a second. An object that nobody owns, that no agency is responsible for, that radar cannot see, that was found by accident by telescopes built to do something else. That is being tracked by volunteers coordinating through a mailing list. That is being pushed off course by sunlight in ways nobody can fully predict. And that nobody, anywhere, under any circumstances could have moved if the geometry had come out slightly differently. Passing within a few kilometres of an operating spacecraft 2 minutes before it hits the moon. We were not in control of any part of that. We were spectators to our own hardware. And a hazard measured in a paper only means something if somebody is counting the events that produce it. The entire counting apparatus for the space between here and the moon is a handful of astrotelescopes doing it as an unwanted side effect, and one man with a mailing list. Part 10. The fix that costs almost nothing. By this point in the video, you have probably formed a conclusion, and I want to take it away from you because it is the wrong one. The conclusion is that this is a hard problem, that it is one of those unfortunate consequences of doing anything ambitious, an engineering challenge that the smartest people in the world are working on and have not yet cracked, and that in a decade or two the technology will catch up and someone will solve it. That is not the situation. The situation is much stranger and much more frustrating than that. The problem is solved. It has been solved for years. It costs almost nothing, and nobody is required to do it. Here is the solution, in Gray's own words. The simplest approach is to put upper stages in orbits where they will leave the Earth and the Moon and end up in orbit around the Sun where they will not hit us for a long time. That is it. That is the whole fix. Instead of abandoning the stage in a high orbit around the Earth that crosses the Moon's path 14 times a year for the next several decades, you spend a little of the residual propellant, or you plan the trajectory slightly differently in the first place, and you send it out into a solar orbit where the nearest thing it might hit is nothing for centuries. And this is not theoretical. Let me give you 3 worked examples, all real, all recent. When the James Webb Space Telescope launched, its upper stage was deliberately placed into an orbit around the Sun, calculated to avoid coming anywhere near us for at least the next 100 years and most likely for thousands. Somebody sat down during mission planning and did that arithmetic on purpose, as a line item, and then executed it. Nobody made them. It was simply considered the correct way to do the job. The second example is the one I find most telling. Recent Chinese lunar launches have put their upper stages into solar orbit. That is a change from their previous pattern, which was to leave stages in orbits where they could eventually hit the Earth or the Moon, and it is exactly that previous pattern which produced the object that made 2 craters on the far side in 2022. The same agency that has never acknowledged that impact appears to have quietly fixed the underlying practice. They did not announce it. Somebody noticed by watching where the stages went. And the third example closes the loop entirely. A Falcon 9 upper stage launched in November 2025 for a science mission heading beyond the Earth-Moon system was placed so that it will end up orbiting the Sun. Gray notes that he gathers from usually reliable sources that the company wanted it that way. Sit with that for a moment. The same company whose stage is going to hit the Moon on Wednesday has, since that launch, deliberately disposed of another stage properly. This was never a capability problem. It was never a physics problem. It is not a technology gap waiting on a breakthrough. The people involved know exactly how to prevent this. They have demonstrated it repeatedly. And the reason it did not happen in January 2025 is simply that nothing required it to. I have to give the honest limitation immediately, because overstating this would be the easy mistake, and it would be a real one. The trick only works for missions that were already going to the Moon or beyond. Those are the only spacecraft with enough energy to escape the Earth-Moon system in the first place. The far larger population of upper stages that go to low orbits cannot be sent to the Sun, because they do not have the fuel and never will. Those stages come back down into our atmosphere, and dealing with that is a genuinely difficult, genuinely unsolved problem, with its own set of concerns about what all that vaporized metal is doing to the upper atmosphere. Gray's own summary of the situation is the thesis of this entire section, and it is worth quoting exactly. Avoiding lunar impacts is pretty easy. Avoiding the stuff that hits the Earth is a much more difficult problem. The lunar problem is the easy one. It is the solved one. It is cheap, it is demonstrated, it has been done at least 3 times by 2 different organizations on 2 different continents, and it is required of absolutely nobody. So why is nobody required to do it? Because there is no mechanism by which anybody could be required to do it. The foundational document for all of this is the Outer Space Treaty, which dates from 1967. It is a genuinely visionary piece of law for its era. It establishes that space is not subject to national appropriation, that celestial bodies are to be used for peaceful purposes, that states bear responsibility for their national activities, including those of private companies, and that parties should conduct their activities with due regard to the corresponding interests of other states, and avoid harmful contamination. Those are good principles. They are also, for our purposes, almost entirely inoperative. The treaty does not define debris. It does not create any obligation to remove it. It does not establish a traffic management authority for the space between the Earth and the Moon, or for orbit around the Moon, or for the lunar surface. It does not set rules for permanent settlements, because in 1967 permanent settlements were a thing you wrote science fiction about rather than a thing you legislated for, and it contains no enforcement mechanism whatsoever that anyone can invoke. The academic literature on this is not subtle about the gap. Recent work in the field states plainly that the existing framework falls short of the demands of cislunar space and proposes what is missing. Cislunar-specific traffic management rules, debris mitigation guidelines written for the lunar environment rather than borrowed from Earth orbit, a high-fidelity catalogue of objects in cislunar space, actively maintained with somebody's name on it, None of that exists in binding form. All of it is a proposal in a journal. Which brings us back to the last paragraph of Wednesday's paper, the one I read to you earlier, and which reads very differently now. To avoid uncontrolled increases in the amount of space debris in lunar orbit, as is the case now in low Earth orbit, advancing monitoring of cislunar space will be key. Notice what they chose as the comparison. Low Earth orbit is not a neutral example. It is the cautionary tale of the entire industry. It is the environment where the International Space Station has had to physically move itself out of the way of debris dozens of times, where collision avoidance maneuvers are routine paperwork, and where the runaway scenario has a name that every person in the field knows. And there is one structural difference between the two environments that makes the lunar case worse in a specific and underappreciated way. In low Earth orbit, there is a cleaning service and it runs for free. The Earth's atmosphere does not stop at a hard edge. It thins out gradually, and even at hundreds of kilometres up there is enough of it to exert a very slight drag on anything moving through it. Over years and decades, that drag pulls debris down, and when it comes down far enough, it burns. That process is slow, it is unreliable, and it does not work at all for objects in higher orbits. But at the altitudes where most of the junk is, it runs continuously, and it has been running since the first satellite went up, and everything currently in low orbit is on a clock because of it. The lunar surface has no clock, no drag, no decay, no burn-up, no wind, no water, no weathering, no subduction. Nothing gets swept away, nothing settles into a seabed, nothing gets buried by anything except the next impact. The equivalent process does not exist and cannot be engineered into existence. Which means that in the one environment where debris is genuinely permanent, we have the least oversight, the fewest rules, no catalogue, no authority, and no obligation. And I will let Bill Gray have the last word on this section, because his phrasing is more restrained than mine, and it lands harder for being so. The impact, he writes, does not present any danger to anyone, though it does highlight a certain carelessness about how leftover space hardware is disposed of. Carelessness, not conspiracy, not negligence in the legal sense, not malice. Just the ordinary, unremarkable carelessness of a system in which nobody was ever assigned the question. That is the reason a rocket hits the moon on Wednesday. Not because the 1,000-kilometre hazard was assessed and accepted, because no one anywhere was required to assess it. Part 11. But the rocks are worse. Now I am going to argue against everything I have just told you. Not because I have changed my mind, but because there is a strong objection to this entire video, and if I do not put it to you in its strongest possible form, then I am not doing my job. There are people watching this right now who already know what I am about to say, and who have been waiting through the last hour for me to get to it, and they are right to have been waiting. The objection is this. The moon gets hit constantly. It always has. Everything I have described is a rounding error against the natural background, and worrying about it is like worrying about the litter on a beach during a hurricane. Let me make that case properly, with numbers, because it deserves better than a straw man. Meteoroid impacts have been the dominant process shaping the lunar surface for billions of years. Not one of several processes, the dominant one. Every crater you can see through a pair of binoculars, every ring and basin and scar on that face, is the accumulated record of things hitting it. Since 1999, several hundred impact flashes have been recorded from Earth by telescopes specifically watching for them. The brightest reach magnitude +3, which is bright enough to see in a small telescope. The objects causing them are typically sub-kilogram rocks, arriving at tens of kilometres per second, sometimes as fast as 70. That is happening right now. It happens every night. Nobody stops it. Nobody could stop it, and any structure ever built on that surface has to survive it. And then there is the comparison that really does the damage to my argument, and I am going to give it to you exactly as the man who found Wednesday's rocket gives it. In the spring of 2024, a natural impact excavated a crater on the moon 225 metres across. 225 metres. Wednesday's impact is expected to make a hole of somewhere between 17 and 30 metres, so the natural event was roughly 10 times the diameter, and because ejector scales with volume rather than width, it threw out something on the order of 1,000 times more material. One natural impact 2 years ago, that nobody predicted, that nobody watched, that made essentially no news, did 1,000 times more of exactly the thing this video has spent an hour worrying about. Gray's conclusion is blunt. The dangers from natural impacts would still dwarf those of artificial ones. He is right. I want to be completely clear about that. He is right. It is not close, and any lunar base that ever gets built will have to be engineered against the natural background, regardless of what humanity does with its rocket stages. If you shut down every launch program on Earth tomorrow, the moon would carry on being bombarded exactly as it has been for 4.5 billion years. So why am I still making this video? 4 reasons, and they are not about magnitude. Every one of them is about structure. The first is that artificial impacts are chosen. You cannot negotiate with a meteoroid. There is no committee you can petition, no policy you can change, no line item you can fund that will reduce the natural impact rate by even a fraction of a percent. It is a fixed feature of living in a solar system, and the only rational response is to build accordingly. But every single artificial impact is the downstream consequence of a decision that a specific person made on a specific day about what to do with a specific piece of hardware. And as we established in the last section, the alternative decision costs almost nothing and has already been demonstrated 3 times over. You cannot negotiate with a rock. You can absolutely negotiate with a launch manifest. The comparison to the natural background answers the question of whether artificial impacts are the largest hazard. It does not touch the question of whether they are an acceptable one. Those are different questions, and only one of them has anything to do with size. The second reason is that artificial impacts are not randomly distributed. Natural impacts land anywhere. The distribution is essentially uniform across the surface, with only slight variations from orbital geometry. A meteoroid has no opinion about where the interesting real estate is. Human hardware does. Artificial objects arrive in the space around the moon because we sent them toward things we care about, and we're about to start caring very intensely about a small number of specific places. The traffic concentrates where the interest concentrates, and as we're about to discuss, the interest is concentrating very sharply indeed. A uniform hazard and a clustered hazard of the same total magnitude are not the same hazard at all. Ask anyone who has ever had to site a building on a floodplain. The third reason is that artificial impacts are the wrong physics, and this one is more technical, but I think it is the most interesting of the 4. The paper puts it in a single sentence. This object is significantly more massive than most natural lunar impactors, but is also moving much more slowly. Both halves of that matter, and together they produce the worst possible combination for debris. A natural impactor is typically a sub-kilogram rock moving at 30 kilometres per second. Enormous velocity, tiny mass. Most of the energy in that collision goes into a violent, superheated, supersonic shock. A lot of it comes out as light, which is why we can see those flashes from here at all. A lot of it goes into vaporizing both the rock and some of the ground. Wednesday's impactor is 4,000 kilograms moving at 2.4 kilometers per second. Enormous mass, comparatively modest velocity. Below or barely above the sound speed in the target material, as we discussed, so much less of the energy comes out as light, which means much more of it goes into the only other place it can go, moving rock. The quiet impacts are the dirty impacts. An artificial impactor is systematically worse at producing a flash, and systematically better at producing debris per unit of energy than a natural one. It is the difference between a bullet and a boulder. One makes a spectacular hole, the other moves the hillside, and the fourth reason is short, and it is the one nobody expects. Rocket stages can explode. The paper says it in one clause, tucked into a section about impact energies. Any unspent fuel in rocket stages may explode upon impact, resulting in greater energy release than from a natural object of equivalent momentum. Natural rocks do not carry residual propellant. They arrive with kinetic energy and nothing else. A spent stage arrives with kinetic energy plus whatever chemistry is still sitting in the tanks. And while a stage this old is very unlikely to have much of anything left, the general case is that artificial impactors have an additional energy source that natural ones categorically do not. So those are the 4 structural differences. Chosen rather than unavoidable, clustered rather than uniform, slow and heavy rather than fast and light, and chemically loaded rather than inert. But the argument that actually answers the objection is none of those. It is the 5th one, and it is about time rather than physics. The natural background is constant. It has been roughly constant for billions of years. It is constant now, and it will be constant for the rest of the time anyone reading this cares about. That is a known, stable, characterizable baseline. Engineers love baselines. You can design against a baseline, budget for it, write it into a requirements document, and then stop thinking about it. The artificial rate is not a baseline. It is a function of launch activity. And launch activity has increased by orders of magnitude in a single decade, and every serious projection has it increasing further. More lunar missions are planned for the next 10 years than flew in the entire 20th century. Every one of those missions has an upper stage. Every one of those upper stages has to end up somewhere. Here is the thing about a hazard that is currently 1% of the background. If it stays at 1%, it is irrelevant and nobody should give it a second thought. If it doubles every few years, then in 20 years it is not 1%, and there was never a specific moment when anybody noticed it crossing over, because nobody was measuring it. And that is the actual finding of this video more than any single number in it. We do not know the rate. There is no published estimate of how often artificial objects will hit the moon over the next few decades. Not a bad one, not a rough one. None. The entire public forecast consists of one astronomer saying he is currently tracking about a dozen high-flying derelict objects, none of which presently look like they will hit anything, and that he is keeping a multi-year eye on the upper stage of a Chinese rocket launched in 2013, which does not currently look like it will hit the Earth or the Moon, but which he intends to watch anyway. That is it. That is the state of humanity's knowledge about how often its own garbage will strike the world it is preparing to inhabit. And Gray's own framing of the question, when he was asked about it, was not a prediction. It was a question. How often might this happen? He does not know. Nobody knows. And the reason nobody knows is not that it is hard to work out. It is that it has never been anybody's job to work it out. Which brings us to the part that decides whether any of this matters at all. Because a hazard is only a hazard if there is something in the way. So let us talk about where we intend to live. Part 12. Where we are going to live. Two lunar programs, run by rival powers, working independently in competition, with almost no coordination between them, have arrived at the same conclusion about where to build. They want the same piece of ground. The American plan is called Artemis Base Camp, and it is intended for the lunar South Pole region. The leading candidate area is the ridge system running between Shackleton Crater and de Gerlache Crater, and the reason is a piece of geography so useful it borders on the miraculous. The Moon's axis is almost perfectly upright relative to the Sun. It has essentially no seasons and no axial tilt worth mentioning, which means that at the poles there are elevated ridges whose summits catch sunlight for more than 90% of the year. Almost perpetual daylight, almost perpetual power, from solar panels that barely ever go dark, on a world where the ordinary night lasts 14 days and freezes everything that is not actively heated. And immediately beside those permanently sunlit ridges are permanently shadowed craters, floors that have not seen direct sunlight in billions of years, sitting at temperatures near absolute zero, believed to contain water ice. Water is not just water. Water is drinking water, and breathing oxygen, and radiation shielding, and, split into hydrogen and oxygen, rocket propellant. A base sitting on accessible ice does not have to lift any of that out of Earth's gravity well, and the cost of lifting things out of Earth's gravity well is the single dominant constraint on everything humanity has ever done in space. So, perpetual sunlight for power, and ice within reach for everything else, in the same location. There are only a handful of ridges on the entire Moon where both of those are true, which is why the International Lunar Research Station, the program led by China with Russia, and a coalition of partner states, is targeting a south polar base of its own by around 2035. One of its missions is surveying water ice around Shackleton, the same crater. Another is scheduled to test construction techniques using lunar soil, which is what you do when you intend to build something permanent rather than visit. Both programs, same pole, same handful of ridges, same ice. Now let me handle the schedules honestly, because this is where a video like this could very easily overclaim. The Artemis program was restructured during 2026, with the third mission reframed around a dual lander demonstration in the late 2027 timeframe, rather than the surface landing it was originally advertised as. These dates have moved repeatedly, in both directions for a decade. Anyone who tells you they know the year humans next walk on the Moon is telling you about a plan, not about the future. So I will give you the honest version. Crewed surface operations are now a matter of the late 2020s. Permanent infrastructure is a matter of the 2030s. Those are targets, not facts, and they will move again. But the direction is not in serious doubt. 2 major powers, multiple commercial operators, and more than a dozen partner nations are all moving toward the same small region of the same world, and they are doing it on a timescale of roughly 1 decade. Which brings me to the number I have been holding back, and I'm going to give it to you straight before anybody accuses this video of scaremongering. Wednesday's impact point near Einstein crater is roughly 3,300 kilometres from the lunar south pole, measured over the curve of the surface. That is more than 3 times the modelled maximum ballistic range. This impact cannot reach the places anyone plans to build. Not the fastest fragment, not the finest dust, not under any assumption in either paper. If you take nothing else from this video, take that. Wednesday's collision poses no threat whatsoever to Artemis Base Camp, to the International Research Station, or to any human being alive. Now here is why that number is closer to the margin than it sounds. The Moon's entire circumference is about 10,900 kilometres, so a 1,000-kilometre hazard radius means that the safe separation between an uncontrolled impact and a settlement is roughly 1/10 of the way around the entire world in every direction at once. On a body that's small, far away is not a large category. There is not much Moon left over once you have drawn that circle, and remember this second of the 4 structural differences. Artificial objects do not land uniformly. They arrive because we sent them, and increasingly we are sending them to one specific place. The impacts and the infrastructure are being drawn toward the same coordinates by exactly the same logic, which is that there are only a few good spots and everybody wants them. Wednesday's rocket landed 3,300 kilometres from the base camp by pure chance. Nobody arranged that. Nobody could have arranged otherwise. That is really the whole point. Let me bring back the man who wrote the sentence this video is built on, Benjamin Fernando, explaining why his team cared enough to organise 23 scientists around a piece of falling garbage. Now that we're in an era where we are going to have more and more astronauts going back to the Moon, perhaps permanently, we also want to understand how much of a risk these artificial impacts pose, perhaps permanently. That is the phrase that changes the calculation, and he chose it deliberately. And then the distinction that I think is the most important single idea in the entire paper, after the 1,000 kilometres itself. This, he says, presents a different set of hazards than the Apollo astronauts faced on the lunar surface from the average background meteoroids that are striking the Moon every day. And what the team wants to do with this event is understand both the direct and the indirect hazards. Direct and indirect. The direct hazard is the one everybody imagines, and it is the one that is genuinely almost impossible. A piece of rock, travelling ballistically for hundreds of kilometres, happening to come down on a specific person standing on a surface with the area of Africa and Asia combined. The odds against that are enormous, and nobody serious is worried about it. The indirect hazard is the one that matters, and it is far less dramatic and far more likely. It is the plume coming back down, not on a person, on a habitat, on a radiator panel that has to shed heat continuously, or the interior temperature climbs past survivable, on a solar array that has to stay clean, or the power budget collapses, on an antenna, on a landing pad, on the outside of a spacesuit that has to seal perfectly against hard vacuum for 6 hours at a stretch, over and over again for years, with joints that were already failing after 3 days in 1972. That is what an indirect hazard is, not a rock through the roof, a slow, cumulative, unglamorous degradation of the equipment that stands between a human being and the vacuum. Now let me give you the counterweight, at full strength, because this channel does not get to argue in one direction only. The man who found this object does not think anybody should be alarmed. He has said so publicly and repeatedly, and here is exactly what he wrote. Some of that shrapnel could conceivably go flying around and hit one of the Chinese lunar landers. It is very long odds against it. None of them are close to this spot. He does not think it raises the usual risk level of being on the Moon noticeably. And then, the sentence that is the hinge of this entire video. If we have humans on the Moon in the coming years, we might start to worry more about this sort of thing. But it will not be a problem on the 5th of August 2026. Read those two people's positions side by side, because at first glance they look like a disagreement, and they are not one. The tracker says this event is harmless. He is right. The hazard modeler says this class of event presents a significant hazard to future astronauts and infrastructure across much of the lunar surface. He is also right. They are not describing different risks. They are describing different decades. One of them is describing a moon with nothing on it, where a 1,000-kilometre debris field lands on 3,000 square kilometres of grey rock that has been undisturbed for 4 billion years and will be undisturbed for 4 billion more, and where the only consequence is a new crater in a catalogue of craters. The other is describing a moon with people on it. The gap between those two moons is about 10 years, and the rules that will govern the second one are being written right now, by not being written at all. Because here is what this whole story actually reveals, and it is not what the headlines have been saying. We built the ability to predict this collision to within a fraction of a second and a few hundred metres, 11 months in advance, using volunteer observations and software, one man wrote himself. We built the ability to model the crater, the plume, the velocity distribution, the flight times, and the maximum range of every fragment large enough to see. We can tell an amateur astronomer in Ohio what frame rate to shoot at and which emission line to filter for to catch something happening 385,000 kilometres away. And we built none of the ability to prevent it, none of the ability to count it, none of the ability to answer for it. We solved the interesting half of the problem and skipped the boring half entirely, which is the most human thing in this entire story. The impact on Wednesday does not reveal a danger, it reveals which half of the problem we solved, and step back far enough, and there is something almost poignant in it. For the whole of human history, everything we've thrown away has landed somewhere we did not have to look at. The bottom of the ocean, a hole in the ground, the far side of a hill. Up into an atmosphere that quietly burns it into a haze so thin we only recently worked out how to measure it. Wednesday is the first time in the history of our species that our garbage arrives somewhere we intend to live, at 5,400 miles an hour, on a world that will never once, in the entire remaining lifetime of the sun, clean up after us. The rock will be there when the last person who watched this video is gone. It will be there when the language we are speaking has no living speakers. It will be there when the continents on Earth have rearranged themselves into shapes with no names, and it will look exactly the same as it does the moment it lands. So here is where I want to leave you. On Wednesday morning, 3 of the largest telescopes on Earth will be pointed at the western edge of the moon. Behind them, several hundred amateur astronomers with cameras running at 20 frames a second or faster will be doing the same thing from back gardens and driveways across North and South America. All of them will be watching a specific point on a specific limb at a specific second that was calculated 11 months ago by one man and a piece of software, and not one of them knows whether they will record anything at all if every instrument comes back empty. No flash, no plume, no signal, nothing at all. Then the first time humanity ever tried to watch a collision it had known about for 11 months, on a world it is actively preparing to live on, with the best equipment it has ever built, it could not see it happen. Which leaves one question, and it is the one I have not been able to put down since I started reading about this. If we cannot see the one we scheduled, how would we ever know about the one we did not?